So I will also talk about GANs, but not noise-to-image GANs, but something called image-to-image GANs. So I will start talking about what's the difference between these types of GANs. I will mention two different architectures for image-to-image translation. So the first one is called pix-to-pix, and the second one is called cycle GAN. I will then go through some different applications of image-to-image translation, like synthesizing T2 weighted images from T1 weighted images, synthesizing CT from MR, synthesizing PET from MR, and etc. I will also show one example of distortion correction and one example of abnormality detection. And I will end by talking a bit about different challenges. So one challenge is to go from a 2D GAN to a 3D GAN. A general problem in deep learning is that if you train a model on data from one scanner, it will not work as well on data from another scanner. And the last challenge, if you train your GAN on controls, can you then actually use it for diseased subjects? So the use of GANs has really exploded during the last years. So this is an overview from a nice review paper that in 2016 there was only a single paper, but then it really exploded in the last years. And the most common application is synthesis of new data, but you can also use image-to-image GANs for segmentation. You can use it for reconstruction, classification, and so on. It seems like the most popular modality is MRI, maybe because you have so many submodalities, but GANs are being used for many different types of medical images. So as Bliss mentioned, if you have a noise-to-image GAN, you always start by generating a noise vector, and then your GAN will hopefully produce a very realistic image. So this person doesn't exist, but it's just a very realistic synthetic face. And every time we send a new noise vector to this GAN, you will get a new realistic image. But image-to-image GANs are a bit different, that you don't send a noise vector, but you send an image to the network and you get another image from the network. And this can be used for different kinds of translation tasks. So you can, for example, convert a horse to zebra. You can convert winter images to summer images. You can convert apples to oranges. So these are some examples from the cycle GAN architecture, which is one of the most popular architectures. So you can basically convert between any two domains that you can think of. And this can be before and after segmentation, or before and after distortion correction, or whatever you can think of, as long as you have two domains. And maybe you have seen that Snapchat has released a number of new filters that can actually do what they call a gender swap. So if you want to see a GAN in action, you can open Snapchat, you can apply this gender swap filter that will convert male to female or female to male. I'm not sure what the exact technique is that they use, but I'm pretty sure it's some kind of image-to-image GAN. And maybe you can tell me who these two persons were, the original images, which person they represent. So who do you think this is? Yeah, so this is a female version of Donald Trump. And who do you think this is? Yeah, so this is a female version of Nigel Farage. So if you want to train an image-to-image GAN, you basically have two options, to use a supervised GAN or an unsupervised GAN. So you have images from two domains that we can call X and Y, and then we can train a GAN to convert from one domain to the other. So here it depends on what kind of data you have to start with. So if you have paired image pairs, paired images, you can train a supervised GAN that can learn from this joint distribution. But it's not always the case that you have paired images. So maybe you only have a number of images from one domain and a number of images from another domain, but they are not really related to each other. Then you can train an unsupervised GAN that also has to learn the joint distribution. So to show an example of this, this is one example of paired images where there is a real correspondence between the two domains. And here's one example of unpaired training images where you just, for example, have a number of photos and a number of paintings. And in some cases, it's not possible to have paired images. For example, for the snapshot filter, you cannot have paired training data of men and women. It's not possible to have that kind of data. So we can think of it like this, that if you have a supervised GAN, you want to learn this blue joint distribution, and you get paired samples from this blue distribution. So then it's not very hard to learn the distribution, but for an unsupervised GAN, you only have samples from the two red marginal distributions. And from these samples, you have to learn the joint distribution. So an unsupervised GAN is a much harder problem, but you can use it for many more applications. So one of the first image-to-image GANs was the pix-to-pix. So you have images in the two domains. They need to be paired and registered. Then pix-to-pix can learn to translate from one domain to the other. So you can, for example, see that you can convert from a street scene to a segmentation of each pixel. You can convert a map to an aerial picture. You can convert day to night, edges to photo, black and white to color, and so on. So the main drawback here is that we need paired images and they need to be registered. So if we want to instead do unsupervised translation, for example, using cycle GAN, we need to learn this joint distribution from the marginal distributions, and this is a much harder problem. So we need some kind of regularization to handle this. So what is used in cycle GAN is that they add a cycle consistency loss. So if you take one image from domain X, you transform it to domain Y, and then back to domain X. It should be similar to the original image. And in the same way, if you translate an image from domain Y to domain X, back to domain Y, it should be similar to the original image. So this cycle consistency loss acts as a regularization to prevent that the training fails. So this is my only math slide, but just to define the loss functions. So we have in cycle GAN we have two generators and two discriminators. So we have one generator that goes from X to Y, we have one generator that goes from Y to X, and then we have the two discriminators. So the adversarial loss function we can write like this, that if the discriminator for Y gets an image from the Y domain, it should return 0 since it's a real image from the Y domain. If the discriminator receives an image that has been translated from the X domain, it should classify that this is a fake image return 1, so that the sum here is 0. So this is the traditional loss function for training again. So then we need to add the cycle consistency loss function. So we start from some image from the X domain, we transform it to the Y domain, and then back to the X domain. And then we take the difference with the original X image. And the other way, we take an image from the Y domain, transform it to X, transform it back again to the Y domain, and take the difference with the original image. And then we use the L1 norm to get the scalar from these two different images. So the full loss function is one adversarial loss for each generator, and then this cycle consistency loss. And lambda controls how important is the consistency loss compared to the adversarial losses. As I mentioned, we're training 2 generators and 2 discriminators at the same time. So we're training 4 convolutional networks at the same time. And this is one example of what the discriminator and the generator can look like. So the discriminator is sort of simple with 4 convolutional layers. The generator is a bit more complicated. So since we have to start from an image, we first have some convolutional layers where we downsample the image. Then we have a number of residual blocks. And then to generate a new image, we need to upsample the result that we get in the middle, so to say. So just to show you one example, so this is the text from the CycleGAN paper that describes the generator. So they use a number of different types of convolutional layers. So for example, this C7S1-K is a layer with, where the filters are 7 by 7. DK is another type of layers where the filters are 3 by 3. Then they have RK for residual layers. They have UK for another type of layer. And then they can write out the full generator using this notation. And it might seem that it's would be very complex to write this as a code in Keras, but actually this code represents the full generator. So for each type of convolutional layer, a help function is defined, and then we can use that help function to add different types of layers. So this small for loop represents the 9 residual layers, for example. So you can write that very compactly with Keras. So these are just to show two of the help functions. So DK, it's a very tiny function that takes K as an argument. So how many filters you want in the convolutional layer, and then the filter size is set to 3, and then you apply some normalization and activation function. The residual layer is a bit more complicated, but the code is still pretty short. So if we look at the discriminator, it only has 4 convolutional layers plus the final classification layer. This is the corresponding text in the paper. So here they write that they use something called a patch GAN, which basically means that instead of directly classifying if the image is real or fake, they first classify every patch in the image. But otherwise, they only use 4 convolutional layers, which you can write like this. And then you can decide if you want to use the patch GAN or if you want to convert the final image to a vector and use a fully connected layer for the actual classification. But this is the whole code for a discriminator, so it's pretty easy to write in Keras. So let's look at some of the applications. So one of the first applications for MR images is to convert between different types of images. So you can maybe pretend that you have collected T1 and T2 weighted images for every subject, but maybe for some of the subjects you cannot use the images because the subject has moved too much. Then you can train an image-to-image GAN to synthesize T2 from T1 or the other way around. Or for example from T1 to T2 flare or from proton density to T2. So in this paper they compare a number of different approaches to perform the translation. And to produce a synthetic T1 or T2 weighted image can also be used to make the registration easier. For example, if you need to register a T1 weighted image to a T2 weighted image, that can be a bit difficult. But if you instead produce a synthetic T2 weighted image, you can register T2 to T2 instead. Or if you want to do segmentation of brain tumors and you only have T1 weighted images for some subjects, you can synthesize T2 and then combine T1 and T2 to perform the actual segmentation. So another application is to go between MR and CT. So in this paper, here they show how to go from an MR image into a synthetic CT image. And this is pretty close to the real CT image. So this can, for example, be useful in radiotherapy, where you need to plan how to treat brain tumor patients. So then you often need a CT volume to calculate the dose you need to treat the patient. And if you can avoid collecting the CT volume, that will save some time and radiation for the subject. So in this paper, they also show that they can go from CT to MR, which is maybe more impressive since the MR volume has more details inside the volume. So this is a good example of the cycle consistency loss. So you start with a real MR image, you go to synthetic CT, and then back to MR from the synthetic CT image. And this image shows the error between the real MR and the reconstructed MR image. So another application is MRI to PET. So in this paper they used ADNI data, and they wanted to classify if a subject is healthy or has Alzheimer's disease. So for most subjects there are MRI and PET data, but for some subjects the PET data is missing. So they trained the GAN to translate between MRI and PET. These are the results for two subjects comparing the real and the synthetic PET images. And then they show that if they add this additional data when training a classifier, that they can actually improve the performance compared to only using subjects that have real MRI and real PET. So here, the GAN, you can see it as a kind of data augmentation that you synthesize PET data for subjects who don't have PET data to have more training data for the classifier. This is one example from my research group where we trained the GAN with T1 weighted images and fractional anisotropy maps from 1,000 subjects in the Human Connectome project. So we wanted to see, can we go directly from T1 to FA without collecting any diffusion data? And it seems like you can get pretty close to the true FA maps without collecting any diffusion data. So we sent these results to a conference, and then the reviewers said, like, okay, you have some nice results, but what is the real application here? So then we show that we can actually use this for distortion correction. So in the Human Connectome project data, you have diffusion data with two phase encoding directions, so left-right and right-left, and they both have pretty strong distortions. So for example, with top-up in FSL, you can correct for this distortion. But the problem is that most datasets do not have two phase encoding directions, and it will double the scan time. So instead, we synthesized an FA map from the T1 weighted image, and this FA map has no distortions. So then we could do a nonlinear registration between one of these two original datasets to this synthetic FA map, and then we can produce a similar distortion correction without doubling the scan time. In another application, we wanted to see if we can revert a phase blurring. So normally you blur the face of every subject before you publish your data. So we wanted to know, is this face blurring enough for anonymization? So here the two domains are the original data without face blurring and the data after face blurring. And then we used CycleGAN to learn to translate between these two domains. And this is only a two-dimensional GAN, so it doesn't use any 3D information. It's only trained on sagittal slices, but still we can sort of recover the phase. So since GANs are so powerful, maybe we need to redefine what we mean by anonymized data. So if we look into a bit more advanced architectures, so instead of learning many one-to-one mappings like T1 flare, T2 flare, and so on, why not use all the data when we try to predict a missing image? So this is the main idea of a GAN, that uses a collaborative GAN to instead of converting from one image to another, you try to use all the available images to predict a missing image. So in this case, they combine the three types of images to predict image number 4. And then they show that this approach gives a smaller error compared to, for example, CycleGAN and another architecture called StarGAN. And another idea is to combine different GANs, since a noise-to-image GAN can be pretty difficult to train due to mode collapse and so on. So instead of directly trying to synthesize data, you can try to do it in 2 steps. So you can use a noise-to-image GAN to synthesize some object of interest, like a binary segmentation mask, and then you can use an image-to-image GAN to transform this binary mask into a realistic image. So this approach was used in this paper. So the first did segmentation of these retinal images to get binary segmentation masks. And then they trained a noise-to-image GAN to produce a new realistic binary masks. And then in the second step, they trained cycle GAN to translate between the binary segmentation masks and the retinal image. And these are some of the synthetic datasets that look rather realistic. And here the advantage is that you know that this is a perfect segmentation of the retinal image, since you have created the retinal image from the binary mask. And they also show that training with the synthetic data and evaluating on the real data gives rather similar performance compared to training only with the real data. So I will now cover a bit of the challenges that we currently have with GANs. So almost all the GAN papers you can read, they use two-dimensional GANs both for synthesis and translation. But in your imaging, we have 3D and 4D data. So you can, of course, apply a 2D GAN slice by slice, but it will probably not give you a perfect 3D reconstruction. It's pretty easy to change the code from a 2D GAN to a 3D GAN, but the memory consumption will really increase a lot. So you more or less have two options to work on sub-volumes or to buy a better computer. So the few papers that have used 3D GANs, they work on sub-volumes, and then they do the translation for one sub-volume at a time. Training the GAN is what takes the most time, but once you have trained it, you can run it on the CPU for the actual translation. So if you think back of the code that we looked at, so we had the conv2D to perform the 2D convolutions. We have conv2D transpose that's needed for the back propagation and upsampling 2D. So to change the code to 3D, we only need to replace these functions with conv3D transpose and upsampling 3D. So it doesn't seem very difficult to go to 3D. But if we think of what one convolutional layer looks like, it's pretty common to have something like 256 filters, and then you need to store all the filter responses somewhere. So for one image, that's like 64 megabytes, so it fits on the GPU. But if you have a volume, then it's suddenly 16 gigs. And there are very few consumer graphics cards where you can store 16 gigs in memory. And this is only for a single convolutional layer. So either you have to work on sub-volumes or buy some more advanced hardware. For example, the NVIDIA DGX station, you can have 128 gigs of graphics memory, but that's pretty expensive hardware. So another challenge is that if you train a GAN on data from scanner A and then you try to test it on data from scanner B, it will not perform as well. And this is not specific to GANs, but it's a problem in deep learning. So to show one example, we trained a GAN on 1,000 subjects in Human Connectome project, and then we try to apply it on a completely different data set. And then it doesn't perform as well as before. So there is no easy solution to this problem, but what you can do is to, of course, train the GAN on data from many different scanners, or you can train another GAN to translate between scanner A and scanner B. So you first apply that GAN, and then you need to apply your original GAN. But then you need a lot of images from scanner A and scanner B to first train the additional GAN. So the last challenge that I will mention is that if you train a GAN on healthy controls for image-to-image translation, can you expect that it works for diseased subjects? So in general, you cannot assume that. So in this paper, they show that if they train a GAN for translation between FLAIR and T1, and they do the training on healthy controls, and then they apply it to brain tumor patients, the translation will actually remove the tumor, because the GAN has never seen any tumor. And if they instead train the GAN with images from brain tumor patients and apply it on healthy controls, it can instead add tumors. So when you train a GAN, you have to be a bit careful with what kind of data you use for training and the kind of data you use for the application. So we can see this as a bug or as a feature. So if you have, for example, a real T2 image from a deceased subject, then you can produce a healthy fake T1. And if you also have a real T1 from the deceased subject, you can then make a comparison between the healthy prediction and the real T1. And you can see the difference as some kind of abnormality. But then you can run into registration errors if you don't have a perfect registration. So you don't know if the difference is due to registration or due to a real difference. So what you can do is to go from deceased true T1 to healthy fake T2, and then use the fact that cyclic GAN learns both transformations. So then we can transform it back to T1. And now all these three images are exactly aligned, so we don't need any registration. So there cannot be any registration error. Then we can compare the healthy fake T1 to the deceased true T1. So this is one example where they don't use exactly that approach, but they use something similar. So this is the original data. This is what they call reconstruction, or what I will call a healthy prediction. And then they can take the original minus the prediction, and the difference can be seen as an abnormality. Yes. So we have prepared a notebook that's available on the homepage that you can play with. And otherwise, I can try to answer your questions.
Hi, thanks for the talk. I was wondering, since you spoke about the memory consumption problems, if you go to 3D, if you have considered invertible networks, if you're aware of this option and what you think about it?
No, I have not heard about this.
Okay, yeah, thanks.
Hi. Maybe I saw this wrong, but you showed an image of a GAN that took a T1 image and then produced a CT image and then back to a T1. And the CT image didn't seem to have any brain picture, yet in the synthetic T1, there was a brain again. Is that not a little worrying?
Well, it may seem like magic, but since I guess it relates to the receptive field of your convolutional network. So if it can see the full volume and it knows what the brain normally looks like in MR, you can still make sort of a guess what the brain should look like.
So basically, if I understand correctly, the GAN just made up a brain based on the shape of the skull.
Yeah, it learns what the brain normally looks like in an MR volume. and then it will generate a new brain that fits into your current volume.
But you also had a comparison then, the difference map.
Yeah.
And that didn't show much error. So basically, the invented brain magically matched the original very well.
It looks a bit like magic, but
it does. Thank you.
Thanks for your talk, Anders. I'm wondering, like, for the image-to-image translation stuff, isn't that sort of what UNet does? You put an image in, you get an image out, and usually it's segmentation. But do you have any intuition on why people don't use just UNets to generate modalities and that kind of thing, and where the gain is?
I'm not sure, but I think some researchers seems to use GANs for segmentation instead of UNet. So I think it's more like a matter of taste what you select.